When you hear the word electricity, you might remember the last time you saw lightning in the sky, or the last time you got an electric shock touching a metal doorknob on a dry day. But electricity is all around you every day. In fact, it is also inside you. The activity of all your muscles, including your heart, relies on electricity. So it's not an overstatement to say that your own life depends on electricity. The first electric phenomena to be known date back to ancient Greece. A piece of amber, which the Greeks called electron, rubbed with animal fur, was able to attract light objects, such as feathers. Another example is a piece of glass rubbed with silk, conferring the rubbed object the ability to attract light objects, such as feathers. Also, if you took a piece of glass rubbed with silk and bring it close to a piece of amber rubbed with fur, you would notice that they attract each other. These phenomena were known for centuries but were not really understood. The first attempt to understand these phenomena was put forth by Benjamin Franklin, trying to relate the atmospheric electricity during thunderstorms with the small-scale electricity, such as that of sparks between moving parts. His hypothesis was that object could be imbued with an electric fluid, and some object had an excess of this electric fluid, whereas some object had a deficit of this electric fluid. And when an object with an excess of fluid met an object with a deficit of fluid, there would be a transfer of electric fluid from one object to the other. This idea is actually incorrect, but was a fundamental stepping stone in our understanding of electricity and the modern concept of electric charge. So, what is charge? Charge comes along with matter itself. An atom is made of a nucleus surrounded by an electron cloud. The nucleus is an assembly of particles called protons and neutrons, and the electron cloud is made of particles called electrons, which are much lighter than either protons or neutrons. The charges of protons and electrons have opposite signs. The proton is a positively charged particle, the electron is a negatively charged particle, whereas the neutron has no charge whatsoever. In fact, the proton and the electron attract each other, and the attraction is responsible for keeping the electron cloud around the nucleus at all times. The proton and the neutron interact in a different way than the electron and the proton, and that kind of interaction has very little to do with electricity. In fact, is called the nuclear force. So going back to protons and electrons, they have equal and opposite amounts of charge. This amount of charge is called elementary charge, denoted with letter E, and equal to 1.602 10 to the negative 19 coulomb. So 1 coulomb is a unit of charge. It is a really large unit, and in fact you can see from some examples, balloon rubbed on hair has a net charge of 5 10 to the negative 7 coulombs, which is less than 1 microcoulomb. A honeybee in flight carries about 50 picocoulombs of charge. The net charge listed in this table is not really a count of all the electrons or protons that are in the material. In fact, in every atom there are an equal number of electrons and protons, so the net charge of an atom is always zero. However, there is a number of electrons that are able to move around in the material, and it is these mobile electrons that are responsible for charging objects. So net charge is either a lack of mobile electrons, in which case we'll say the object is positively charged, or an excess of mobile electrons, in which case we say the object is negatively charged. Mobile electrons can be transferred from one object to the other if given enough kinetic energy to hop out of the material. If you rub glass with silk, electrons go from glass to silk. So glass got positively charged at the end of the rubbing process. If you rub amber with fur, the electrons go from fur to amber. So amber got negatively charged at the end of the rubbing process. If you remember, earlier we said that rubbed glass and rubbed amber attracted each other. More generally, positively charged and negatively charged objects will always attract each other. Let's denote charges with letter Q that historically comes from quantity of electricity. So let's say we have two charges, Q1 and Q2. If they have the same sign, they will repel each other, and if they have opposite signs, they will attract each other. Charges obey this property called quantization of charge, that every detectable amount of charge is always an integer multiple of the elementary charge. The reason is that the net charge is an excess or lack of mobile electrons, and the number of mobile electrons has to be an integer. There cannot be a fractionary number of electrons. Another important property of charges is conservation of charge. Charge cannot be created or destroyed, but only transferred between objects. The algebraic sum of all the charges in a closed system of objects is constant. So when you, for example, rub a glass with silk, you're adding electrons on one object, removing electrons from the other object, but not changing the total number of electrons.